Hi, my name is Craig Shultz, and I'm going to talk to you today about TriboTouch, micro-pattern surfaces for low-latency touchscreens. This work was performed by myself, Daehwa Kim, Karan Ahuja, and Chris Harrison at the Future Interfaces group at Carnegie Mellon. The motivation for this work is drawn from everyday touch interactions with devices such as tablets and smartphones. The performance of touchscreens have greatly improved in the last decade by almost every metric except one, round-trip dragging latency. Prior work has shown that users can detect as little as a single frame's worth of latency on a 60 Hz screen. Despite this, modern touchscreen interfaces always seem to lag the user. This is especially true for dragging actions like drawing or scrolling. We believe that this breaks the illusion of a direct manipulation interface in much the same way as being able to see a digital pixel breaks the experience of using a visual display. And we think there's a large benefit to achieving imperceptible latency. The contributions from this work are twofold. One, we introduce a novel hardware concept for capturing touch velocity input. And two, we combine this hardware with a software method for reducing touchscreen latency. Our method relies on the principle of frictional interaction. When two objects slide against each other, friction creates vibrations that are related to 1, the average spatial wavelength of the surfaces, and 2, the sliding velocity between the objects. We can sense these vibrations with the piezo and infer information about sliding velocity by knowing something about the spatial wavelengths. What do I mean by this? Say we have a texture, and this texture has a bunch of bumps on it, spaced about 5 microns apart. If we take another object, like a finger, and slide this along the surface with an unknown velocity, we can then look at the vibrations that are induced and back out the original velocity, all by knowing the pitch or wavelength of the textured elements. It's sort of like a zipper moving up and down. Let's look at what this looks like in practice. Here we're looking at a live spectrogram of the vibrations occurring on the touch surface. I can take my finger, a stylus, or a tangible and translate it around the screen, and you see high-frequency peaks being emitted that relate to the velocity. Purely horizontal or vertical swipes manifest as a single dominant frequency, while circles and more complex movements result in intermodulation and many frequencies being emitted. To understand how movement affects the spectra, we conducted a controlled experiment with a stylus driven by a CNC platform. We adjusted the velocity magnitude and velocity angle and recorded a spectra of vibrations. The left side shows what happens when we increase the linear velocity along the horizontal axis. We see a primary peak in the spectra, which literally corresponds to the velocity divided by the wavelength, 5 microns. For instance, 102 millimeters per second divided by 5 is just over 20 kilohertz, and that's where we see the primary peak. The right side shows the result of an angle experiment. As we increase the angle away from horizontal, we see more complex intermodulation and frequencies which appear to swap. We present a theory for this spectra in the paper. While these spectra were simple to see with CNC-controlled velocities, they are much more complicated with real-world movements. For this, we developed a machine learning approach. We built the prototype touchscreen system, which takes in acoustic vibration data at 192 kilohertz with a mean latency of 27 milliseconds. The native touchscreen reports capacitive touch at a rate of around 60 hertz with 69 milliseconds of latency. We then fuse these two data streams together in a machine learning model and make a prediction of touch location. We draw UI visuals to the screen using this predicted position. Round-trip latency is about 96 milliseconds for this system. That means when we receive new touch data, we have to predict this far into the future just to stay present, as that data was really 96 milliseconds in the past. Here are some examples of our system in action. We can see that the lag of a conventional touchscreen can be compensated for by applying this technique. We believe this enables a better user experience where elements seem to flow from the user's finger and actions are locked to finger location. We also believe that it can benefit tangible screen interactions as tangibles also seem stuck to their graphical counterparts. To evaluate this technique, we collected data from a group of 11 users. We gathered touch and acoustic vibration data while participants completed 3 tasks: drawing shapes, writing words, and targeted dragging. Each participant completed 108 actions. We then looked at the mean Euclidean error, that is, how many millimeters off our prediction was from the actual touch location. And we see that our acoustic plus touch machine learning model in purple results in the lowest error, and this holds true for any value of compensated latency we tested. To summarize, we introduced a novel hardware sensing technique which senses vibrations produced from an object's rubbing on a micropattern surface. We characterize how these vibrations change depending on the velocity magnitude and angle. We developed a prototype touchscreen system in which we fused our new technique with capacitive sensors and machine learning methods. We tested this against real-world touch input and showed an improvement over using touchscreen data alone. Thank you for your time.